Hi again. So in the previous videos, we started talking about complex numbers, and essentially, so we define a complex number as an object of the form z equals a plus ib, where I is a unit imaginary number such that I square is minus of 1, and a and b are real numbers or belong to real numbers. And then for this composite object of the form a plus ib, we sort of started defining certain rules for how to add two complex numbers, to multiply complex numbers, subtraction and division. And it turns out that with those rules, we can think of such an object as numbers, because they satisfy all the rules that we've associated with objects that satisfy all the rules that we associate with objects being defined as numbers, which is what we talked about in one of the earlier videos, and I'll put a link just to review those ideas if you like. So hence such an object that seems to be composed of two parts, and hence the name complex, is a number because it satisfies the rules that we have chosen to define an object as a number. Okay, now, however, the rules of addition and multiplication that we, or the definitions that we gave for addition and multiplication, they're sort of like definitions, and they don't yet have an interpretation. And this is what sort of, even historically, like, people found it very hard to accept what a complex number is, because they couldn't, it wasn't easy to visualize or to interpret what this addition or multiplication rule is really doing. And this is where a key idea by, amongst other people, by Wessel, Argun, and a lot of weight added by Gauss, sort of led to the, so they proposed a very key idea, which is to think of complex numbers as points on a two-dimensional plane. And this geometric interpretation turned out to be one of the main factors why eventually complex numbers gained widespread acceptance, and in fact sort of adds, and in fact it's one of the it's become a very essential part of studying complex numbers, functions, and how they sort of behave. Leads to a very rich geometry of the plane. So we'll talk a lot about these ideas, but the basic idea behind thinking of complex numbers as points on the complex plane essentially comes from the fact that we can think of a complex number as composed of two real numbers. In this case, we have chosen to label them as a and b, so we have two real numbers, a and b. Now, two real numbers can be represented, one of the ways of representing two real numbers is to think of them as a point in a two-dimensional Cartesian plane. So if you draw the Cartesian plane, we have one axis here, one axis here. Now, typically, when we are labeling vectors on a two-dimensional Cartesian plane, we think of this as the x-axis and think of this as the y-axis, right? And then if we were to label a point, let's say a vector r, which is x units along the x-axis and y units along the y-axis, here ex hat and ey hat are unit vectors along the x and y direction. So this is like a vector with it's a two-dimensional vector space with bases ex hat and ey hat. So if you are to label a vector r on a Cartesian plane, then we'll move x units along the x-axis and then y units along the y-axis, and then label this as the vector r, where this is the origin, 0, 0. So this is the typical representation of a two-dimensional vector on the Cartesian plane. Now the idea is to, since a complex number seems to be composed or is composed of two real numbers of the form a and b, we can also try to represent a complex number on such a two-dimensional plane. And then what we'll do is we'll simply relabel the axis, where the horizontal axis we can call as a real axis, and the vertical axis we'll call the imaginary axis. And if you want to label a complex number of the form a plus ib, then we move a units along the real axis and then b units along the imaginary axis, and we arrive at the point z, which is a plus ib. So if we just take the Cartesian plane and start labeling points, start labeling complex numbers onto it, such a plane is called the complex plane. And hence the name for this particular discussion. So now we have a complex plane where the complex number z can be represented, complex number z of the form a plus ib can be represented as a units along the real axis and b units along the imaginary axis. Now, just to make this, take some examples, one of the ways of drawing or labeling points on this complex plane, just to make it more transparent, is to think of this as, say we label points 1 units along the x-axis. So we move 1 unit here. Similarly, this is 2 units along the x-axis. This could be 3 units along the x-axis. Now, if we move along the vertical axis, then we label points as, so if we move 1 unit, we arrive at the point 0, I. If we move 2 units, we'll arrive at the point 0, 2i, and 3 units 0, 3i, and likewise it extends in the negative direction. So here we'll have -1, 0, -2, 0, -3, 0, and so on, and then we'll have 0, -i, 0, -2i, and so on. So this is sort of the labeling. If we label the two axes that we typically use for Cartesian plane with these labels, I've just chosen integer points for convenience. Of course, all real numbers on the real axis and all real numbers on the imaginary axis, they're all part of this description. So let's say we were to arrive at the point. Let's say we were to think of where is the point z, which is 0 plus I, right? So if you think of this in terms of the two real numbers, then a is 0 and b is 1, and so we arrive here, right? So we move, so the real part of this complex number is 0, and it has 1 unit along the imaginary part, and so we arrive at this point z. If we were to arrive at the point, let's say z equals 2, then we notice from this that it does not have an imaginary part, and so we just move 2 units along the imaginary along the real axis and arrive at this point. If we are to label a point 2 plus 3i, so let's say you want to arrive at the point z equals 2 plus 3i, then you'll move 2 units along the imaginary axis, along the real axis, and 3 units along the imaginary axis to arrive at this point. Okay. And if we are to arrive at an arbitrary point, let's say z equals x plus iy, then we'll simply move x units, let's say this is x units along the real axis and y unit along the imaginary axis, which could be somewhere here, for instance, and we arrive at the complex number x plus iy. Okay. So having arrived at this point, and notice that this point is 0 units along the real axis and 0 units along the imaginary axis, so this is the origin. So this is origin. Okay. Now having arrived at this point, we can now think of this point also in terms of vectors. So for instance, the vector drawn from the origin to this point should be a straight line. A vector drawn from the origin to z equals x plus iy would be an arrow drawn from the origin to the point z. And with the notion of vectors, we can also define the length of this vector and the angle that this vector makes with the x-axis. So the length of the vector in terms of complex notation is, so for instance, we can write the length of the vector r, and this is typically denoted as the modulus of z. So we write z enclosed within 2 vertical lines. It's called the modulus of z. This is called modulus. Modulus of z is the length of the vector from the origin to the point z. And since this is y units and this is x units, so this is x and this is y, the length in this case would be simply square root of x squared plus y squared. Okay, and this is a very important idea that the modulus of a complex number of the form x plus iy, whenever we can represent a variable or a complex number in the form x plus iy, then its modulus is square root of the real part of the complex number squared plus, which is x squared, plus the imaginary part of the number, which is y squared. Notice that it should not be x squared plus I squared y squared. That will lead to x squared minus y squared. That's not the modulus. The modulus is the real part, which is x, and the imaginary part, both of which are real numbers. So the modulus is x squared plus y squared, square root of the whole expression. That's the modulus. And similarly, we can define the angle. If this is making an angle of theta, then tangent theta is y over x. The y is again the imaginary part of the complex number, and x is the real part. And this is sometimes called the angle theta is called the argument of the complex number z, where ARG stands for argument of the complex number z. So there are two important points: the modulus and the argument of the complex number z, which comes about naturally when we think of z as a point in the two-dimensional complex plane. Okay, so this is the basic idea behind the complex plane. And now in the next part of the video, let's see what the addition of complex number means geometrically, and then we'll talk about multiplication and a few other ideas. So see you in the next part. Thanks.